Hi everyone, I welcome you to the fourth lecture of on thermal properties of matter. So today I will be going to discuss some of the concept related to the heat capacity. So this time I'm not saying the specific heat capacity, is the concept of heat capacity that I have to go through. Then I will cover the concept of latent heat, and then we'll cover different modes of heat transfer. Okay. First I will be going to discuss capacity. Heat capacity. So it is nothing but the amount of heat required to raise the temperature of to raise the temperature of whole body by 1 degree centigrade. Okay. So heat capacity is nothing but C is equals to M into C. So that is, so because we know that when we say it's specific heat capacity, C is specific heat capacity. So when we say specific heat capacity, then it means to say that whenever this word comes, I told you that it's per unit mass, and so the heat capacity is mass into the specific heat capacity. Okay, so that is all about the heat capacity. Now let's look at the concept of latent heat. So what is latent heat? Latent heat. So it is actually amount of heat required. It is actually amount of heat required to change the. It is actually the amount of heat required to change the phase of a material at a same temperature. Latent heat is also defined as per unit of mass. It is also defined as joule per gram per unit of mass. So it's like you need to convert 1 gram of ice to 1 gram of water. So basically, in this, if you're going from 1 gram of ice to 1 gram of water, then it is melting. And if it is you are going from 1 gram of water to 1 gram of ice, then it's a fusion. Okay. So the amount of heat required for this conversion is lambda is equals to 336 joule, and it is generally denoted by lambda. So it's already per gram. So okay. So it is actually the amount of heat required to change the phase of a material at the same temperature, and it is defined as a specific unit, and that's why it's joule per gram. So if you convert 1 gram of ice to 1 gram of water, then the process is called melting. And if you convert 1 gram of water to 1 gram of ice, then it's a, you can also say that freezing. Instead of fusion, it's freezing also. Instead of freezing. So basically we are freezing the water. And the heat is the net amount of heat that is required to change the phase. Net amount of heat required to change the phase of m gram of material, then it is called, then it can be shown as q is equals to mn. So this amount of joule of heat actually required to change the phase. So let's look at some of the question. The question are, find the amount of heat heat required to change 10 gram of ice ice at -5 degrees centigrade to water at 20 degrees centigrade. Sea of water is 4.2 joule per gram degree centigrade. Specific heat of ice is 2.1 joule per gram degree centigrade. In this lambda, there is nothing like degree centigrade because uh, it's this phase change is happening at a particular temperature that is constant. The lambda of ice is lambda for water to ice is 336 joule per gram. Okay, so we need to change. So let's look at the question. So we need to change ice that is at -5 degrees centigrade to water that is at 20 degrees centigrade. So there were many in process happen in between the change from ice to water. Okay, so those are like what happens. You need to understand this phenomena. Like first, because we know the freezing point of ice is 0 degree centigrade, or the melting point of ice is 0 degree centigrade. So ice will go from -5 degree centigrade first to 0 degree centigrade. That is ice only. So that is 0 degree centigrade, and that is happening at a constant. Now the temperature is changing. So when there is a change in temperature, then the heat that is required to raise the temperature, that is called as specific heat. And amount of ice is 10 gram here and 10 gram here. Now we have ice at 0 degree centigrade. Now there is a phase change. So phase change of ice is, so lambda is required. So that is the latent heat. Latent heat is required. So now ice is converted to water, and that is at 0 degree centigrade. As I told you that any phase change is happening at a same temperature. That is 10 gram of water at 0 degree centigrade. Now we need to raise the temperature of water to 20 degrees centigrade. So we need water at 20 degrees centigrade. So that is specific. Now again we need a specific heat. We need a specific heat is required. Okay. So here it's Q. I can call as S. It's phase change. So I'm calling as Q latent, and it is again. So here is QS1 and QS2. So that is due to specific heat. So the total heat that is required to change ice at -5 degrees centigrade to water at 20 degrees centigrade is QS1 plus QL plus QS2. Okay. So QSL is MCP. So CP is C of ice. So that is 22.1 into delta T. So -5 to 0. So final is 0 plus 5. So that is into 5 plus latent heat, that is M, into latent heat that is given, that is 336 joule, plus QS2. So QS2 is, now we need a specific heat of water, M into 4.2, and the temperature changes 20 degrees centigrade. So you can take M to be common. So it will become 10.5 plus 336 plus 84. And what we get is 4. So 336, 420, 420 plus 10.5, 430.5 into 10 joule. So that is 4305 joule. that is the amount of heat required to change the ice at -5 degrees centigrade to the water that is at 20 degrees centigrade. Let's look at another question. Find the amount of heat released when 1 kg of water vapor at 100 degrees centigrade is cooled to is cooled to water at 20 degrees centigrade. Okay. So we have a water vapor. Now water vapor at 100 degrees centigrade. So 1 kg of water vapor at 100 degrees centigrade has to be cooled to water that is at 20 degrees centigrade. So there is two processes happening, that there is a phase change and there is a change in temperature. So whenever there is a phase change is required, so we need to think about the latent heat. And when there is a change in temperature, then it's the specific heat. So let's make a diagram for that how the process is happening. So water vapor at 100 degrees centigrade, so that is at the point at which the water boils, so that is at 100 degrees centigrade. Now from 100 degrees centigrade, for condensation, it needs a water droplet at 100 degrees centigrade, and that will be taken care by lambda. Now this water needs to be cooled down to water that is at 20 degrees centigrade. So here we need lambda, here we need a specific heat. The specific heat of water is given, so that is 4.2 joule per gram degree centigrade, and water vapor is 2260 joule per gram. 2260 joule per gram. It's not a C, it's actually lambda, that is 2260 joule per gram. Okay. So net Q is Q1, Q2. So Q is Q1 plus Q2, so that is M into lambda plus M C dt. So M is nothing but 1 kg, that is M. Lambda is 2260 plus PW is 4.2 into, and the change in temperature is 80. So that is 1000 gram into, so that's direct 8 4 236 plus 2260. Sorry, 336 plus 2260, it becomes 2596. 2596, so it is 2596 kilojoule. Okay. Now let's look another question. A piece of ice of mass 40 gram is added to 200 gram of water at 50 degrees centigrade. Calculate the final temperature when all ice is melted. Given that the specific heat of water is 4200 joule per kg Kelvin, and for lambda for first change is 336 into 10 to the power 3 joule per kg. So now, so we have a water. So we have water at 50 degrees centigrade, and ice is put inside the water. So the temperature of ice is we don't know. We need to find out the final temperature when all the ice is melted. This is the temperature of water. Okay, so there two things are happening. So because it's the hot water, the ice will melt down, and once it's melt down, then in melting it down, the temperature of the water will going to decrease, and due to which we have some another final temperature. Okay, time to put the charger. Okay, so first we have a hot water. So we have a hot water, and mass of hot water is given, that is 200 gram. Temperature is 50 degrees centigrade. Then we have cold ice, that is mass is 40 degrees, mass is 40 gram. So temperature is, because it's ice, so considered it's not given. So it's considered to be a 0 degree centigrade. Now this ice gets melts to a water, so there is a phase change at a constant temperature. And so the lambda is given as 336 into 10 to the power 3 joule per kg. Now here what will happen is the temperature of the water decreases. So that is mCp delta T. So now by the principle of calorimetry, mCp delta T should be equal to m lambda. So this is m of water. So let's call it as 1. Let's call it as 2. This is 2. So that is mCp dt. So m1 is 200 gram. So now we know everything is in kgs. So that is 200 divided by 1000. Specific heat is 4200. The change in temperature. Let's the final temperature of the mixture of this is T. So final temperature is T minus. So we need to check whether this is just equal to this, or there is some amount of heat that is remaining to increase the temperature of this water. So let's consider that case. So there may be a possibility that some amount of heat is required to increase the temperature of this water. Increase the temperature. Okay. So then this will become m1 Cp dt plus is equals to m2 lambda plus m2 C P. No, I don't want to confuse. So let's call it sea water. Sea water and delta T. For this case, the final temperature is, let's say, theta. So M1 is 200. 200 into 4.2, if it's in gram, into delta T. So that is, so consider the final temperature of the mixture to be theta. So theta minus T, so that T is 50 degrees centigrade, is equals to M2 lambda. So M is 40 into lambda, that is given 336 in gram, is 6 plus, so it will go to a temperature from 0 to theta. So the final temperature is, so this will become 50 minus theta because it's on opposite side. 50 minus theta, and this is 40 into theta into 4.2. So just solve this and calculate the theta. So this is the level of difficulty. So I think I have shown you all the three kind of questions that covers most of the concepts. Now I will be going to start another topic. So that is mode of heat transfer. Mode of heat transfer. So there are three different kinds of mode of heat transfer, that is conduction, then we have convection, and then we have radiation. We'll go through all of them in detail one by one. But for now, just as a introduction, I will be introducing you to three different modes of heat transfer. So in conduction, what happens is heat. So here, if you consider this box having a molecules, having a tight, or consider it a solid where there is a tight packed of molecules are there present. Okay. Now if you apply a temperature gradient such that T1 is greater than T2, the heat gets transferred. So because of this molecule has having a higher energy compared to others, this will vibrate and this will collide with this and gives this and this. And so this is the way that conduction is happening, and heat transfer is there. So I can write heat conduction. Heat conduction is a process in which heat is transferred, in which heat is transferred from the hotter part, from the hotter part to the colder part without without involving any actual movement of the body's molecules. Okay, so that is conduction. Now let's look at convection. So in convection, what happens is in convection, there is a actual movement of molecules or due to some mass transfer. So for example, that is boiling of water, boiling of water, or if you see fan, cooler. So these are all the example of the convection. So where there is a some molecules, some surrounding molecules are basically transferring a heat, and this phenomena is generally happened in gases and liquids. And liquids. Okay. Now, the last phenomena, that is radiation. So it doesn't require any transfer. So it does not require any medium to transfer heat. The heat is transmitted in the heat is transmitted via EM waves, by electromagnetic waves. Okay. So that is the that are the three different modes of heat transfer. Discuss about these mode of heat transfer one by one. So the example of radiation is microwave, here example for the conduction is that if you put a pan on a stove, then heat transfer is transfer is due to conduction. Okay. So that are the different modes of heat transfer. So let's first discuss today uh, conduction in some detail. Conduction. So as I told you that conduction is a transfer of heat by the vibration due to the collision of the molecules and without any actual transfer of molecules. So now let's consider let's say some slab. That's a slab such that it these sides are insulated, and we have applied a temperature gradient here such that T1 is greater than T2, and the length of the conductor is, we are considering a conducting slab. So length of the conductor is L. So Q across this conductor due to the temperature gradient, that's a conductor, is Q is directly proportional to area of the cross section. So this area of cross section, Q is directly proportional to the temperature gradient. Q is directly proportional to the time, and Q is inversely proportional to the length of the material. So it will become Q is equals to K A T1 minus T2 into T by L. So that is Q. So the rate of heat flow is rate of, if you want to find out the rate of heat flow, so that is Q by T, and that is K A T1 minus T2 divided by L. And we generally call this to be H. So that is H is equals to K A delta T. If you take delta T, then it will become minus L. We can also write this terms as H is equals to minus K A dt by dx. So if this direction is x, then the temperature gradient in this direction. So that is H is equals to minus K A dt by dx. And that is also called as Fourier law of heat conduction. Law of heat conduction. So either you can take the total absolute temperature gradient, that is delta T by R, or you can take the dt by dx, and then you can find out. Okay. So there are generally two types of conduction processes we learn. Conduction process we see, that is first steady state conduction, and another is transient conduction. So when we are saying a steady state conduction, then it means to say that there shouldn't be any time derivative present in the system. Suppose you apply a temperature gradient on this slab. Okay, so since the T1 is greater than the T1 is T2, so it will goes like this. It will go like this. I will be 1 minute. The temperature profile will looks like this. That is before reaching the steady state. And that's after steady state. As we go along, then time is increasing. And this is the steady state profile. So at a steady state, there shouldn't be any time derivative. However, there is a temperature gradient, and we can directly see that if suppose this is the x direction, then there is a temperature change in temperature with respect to with respect to the position, even at the steady state. So when we are steady state, then it means to say that del T by del T at any x is just 0. So that is the condition for steady state. So the before reaching the steady state, all of these are the transients. So that's a transient state. Okay. So those concepts are not really come in class 11. That is some higher level. Okay. So now let's look at one of the question on conduction. So copper wire, sorry, copper cube of edge length 10 centimeter, temperature at 2 inches at 2 ends is 100 degree centigrade and 0 degree centigrade. Thermal conductivity is, so I forgot to mention, I guess. So this K is nothing but the thermal conductivity. So that's the inherent property of the material. Okay. So here copper cube of edge length 10 centimeters. So that the temperature at the 2 ends is 100 degree centigrade and 0 degree centigrade. And thermal conductivity is given as 400 watt per meter degree centigrade. We need to find out what is the rate of heat flow. So we need to find basically H. Let's try this question. So H is, we know that K A delta T by L. That's the one dimension. We know delta T is 100 degree centigrade. L is, so that is the H length, that is 10 centimeter. So 10 into 10 to the power minus 2. Area of cross section is nothing but the square of this. 10 into 10 to the minus 2 square. K we know that is 400. So everything we know, just substituted and we found it to be 4000 joule per second. Okay. Okay. Now let's take another question. The question is, we have two different kind of system and both are cylindrical in nature. Cylindrical in nature such that we have a unidirectional heat transfer. Okay. So this is 100 degree centigrade, this is 0 degree centigrade. This is L. And we have this area of cross section A and thermal conductivity K. Now we have another system where that is B. So we have the similar system with same area. So we have another system having the same area. The temperature gradients are same, that is 100 and 0. Now length is 4L and thermal conductivity is 2K. However, the area of cross section is same, that is E. So we need to find out M1, and at 0 degree centigrade, it is touched with the ice of mass M1, and here ice at 0 degree centigrade of mass M2. Find M1 by M2. Okay. So in order to solve that, we need to first find what is the ratio of Q1 by Q2. So because this, whatever the temperature gradient is causing the heat, that is that that will be going to use to convert ice into a water. So Q1 by Q2 is, so Q1 is M. So so this Q1 is M1 lambda, lambda of ice divided by M2 lambda. We know lambda is same. So M1 divided by M2 is Q1 by Q2. And we know in terms of heat transfer, so Q1 is nothing but, and both are in a context for same time T, such that, so Q is K1. So what is the formula of Q? So that is K A delta T by L. So Q1 is K1, delta T same for both, A is same by L1, Q2 is K2 by L2. Okay. So M1 by M2 comes out to be K1 by L1 into L2 by K2. So that is, we know K1 is equals to K, K2 is equals to 2K, L2 is equals to 4L, and L is L. So that comes out to be 2L. So M1 divided by M2 comes out to be, it's not L, it's just 2. The correct answer is M1 divided by M2 is 2. So I am repeating this question. So it's a bit tricky question. Not that tricky, just you need to know the all the concepts that we have covered till now, because any concept can be really. So in any coaching, like sorry, not in coaching. So in any exam, any competitive exam, the only difficult thing that they makes is they are combining the concepts. So so if you want to crack that exam, so it's better to go through all the concepts and see and attempt as many questions you can, and keep your mind open so that any concept can become anywhere else. So if you see this, so we have a conduction as well as this, the heat transfer from this conduction is used to use for the melting of ice. So that is the concept. So I told you the concept related it. So that is separate concept and that is conduction, and then they combine the concept and then the question is there. So what we did is here, so we know whatever the Q due to this conduction will used to melt this ice. Okay, so that is Q is M1 lambda. M1 lambda is the heat that is required to melt the ice, M1 gram of ice. So Q1 is M1 lambda and Q2 is M2 lambda. So M1 M by M2 is Q1 by Q2, and we know Q due to conduction is minus K delta T, and time we can also put. The time is same. So that's why K1 by L1 and K2 by L2 is there, and M1 by M2 is 2. So that's the final thing. We'll move along and we'll see the different combinations of the conductor, and then we'll look at the radiation in the next class. Okay, thank you.